All right, continuing on with section 2.3, the function section. So last we left off, we were talking about how a line, A-L-I-N-E, a line is friendly and that it's always a function, and it always is negative infinity to positive infinity for its domain and range, and how you can make a t-table and draw it and kind of prove that. So I'm picking up with that discussion on example 5, and here's 5 types of equations, and we're going to talk about their domain and range and if they're functions or not. All right, so the first one, there's that friendly line, I call it. So x is to the first, y is to the first. I just know that's going to graph to be just a plain old line, just straight as a stick. If you want to prove it to yourself, you could plot some points. A lot of times we use 0, 1, and 2, but that's not necessarily magical. You can use any numbers you want. Just plot some points that you can draw on your graph paper or sketch on your paper that will fit. I might not want to plug in 100 because then I'd have to graph it, right? So that's harder to get on my piece of paper. But I can plug in 100. I can plug in negative 100 if I want. You can plug in anything you want to this t-table. In this first example, y equals x plus 4. If I plug in for x, it's probably a little easier. You can plug in on the y side if you prefer, but usually this is solved for y. It's easier if I plug in for x. So that would give me y equals, plug in 0 for x, y equals 0 plus 4, which is 4. And then that's a coordinate. I can plot the point 0, 4. I can plug in 1 for x, then it'll be 1 plus 4, or y equals 5. There's another point to plot. 2 would make it 6. Okay, just to be silly, plugging in 100, because I can. 100 plus 4 is 104, but I'm going to have a hard time kind of drawing it on my paper without kind of counting my tens or something, which you can do. Negative 100 plus 4, let's see, is that negative 100 plus 4 is negative 96. I think that, no, it's negative, oh shoot. Y would be negative 100 plus 4. I don't know why that caught me off guard. Negative 96 was okay. All right, so that would be another point. And on we could go. Plugging in fractions if you want to. You can plug in a fraction. You can plug in a decimal. You could plug in a square root if you felt like it. Anything goes. Plugging in for x. And that's what we call domain, is what can you plug in for x. And it gives you a real output when you work it out over here. Now, when I graph it, then I go into looking at it visually. Now, again, I'm not going to want to plot those because I'd have to go back 100 and down 96 places to plot that. So I'm probably going to plot these nicer ones. 0 and 1, 2, 3, 4. There's a point. And this one is over 1 and up 5. There's a point. That's good enough. That draws that line. So the other way to think about domain and range is when you look at it visually, it's going left and right because there's arrows that show this thing keeps on going left and right without bound, and then up and down without bound. And so we would say the domain is negative infinity this way to positive infinity this way, and the range negative infinity to positive infinity, same thing. And you can also kind of see that on my t-table. Anything goes for either one. It is a function, yes, because the vertical line can only hit it one time. There's no repeating the x value. Also on the t-table, these are just some samples, not exhaustive, but it looks like the x values do not repeat. So it's a function. All right, so that's the friendly line. Well, the bad news is they're not all friendly lines. So sometimes there's radicals and fractions and things. Those are kind of the two main things that cause hiccups in the domain and range, not just being anything goes. So let's talk about this radical example. On the radical, again, your goal is what can you plug in for x that keeps the answer for y real. So, first thing I probably think about is 0. If I try plugging in 0, will it give me a real answer? And it actually does not. If you plug in 0 for the x, 2 times 0 minus 1 is negative 1. That's actually imaginary, right? So you cannot have an imaginary answer and it be in the domain. Domain is what keeps a real answer for y. So we could say that's not in the domain. That it does not make the cut. So what does make the cut? What's the first number you can plug in for this thing and get a real answer? The procedure for figuring that out, I'll tell you is you got to say, well, what would make that equal 0? We got to keep the stuff under the radical greater than or equal to 0. So you say, if it's a radical problem, say what makes that greater than or equal to 0? Because we know when we're less than 0, we're a negative number, making it imaginary. So that's the big deal with a radical. You know, with a square root, you can't have a negative under the radical. So we solve this by throwing the 1 across the line and dividing by the 2, and then it tells you the domain to keep this thing greater than or equal to 0 is going to start at 1/2. You can equal 1/2 or greater than 1/2, and that's how we would write the domain. We would put a bracket. Remember from our earlier lessons, a bracket means that you actually include that in the solution. You can use 1/2, and then anything larger than that, so to positive infinity. And we could prove that on our little t-table thing. You could plug in a half. When you plug in a half, you're going to get an okay answer. You're going to get 2 times a half minus 1. Let's see, that's 1. 1 minus 1, so you get square root of 0, which is real. You can do that on your calculator, and it works. Square root of 0 is 0. So that answer gives us a real answer for y. So that is the start of our domain. And then you can plug in 3/4 if you felt like it, or 1 would probably be more reasonable. Maybe you plug in 1 and 2, but anything bigger than a half, and a half included. So what is the range? What was the smallest value you get for y? And that is that 0. When we plugged in that 1/2, the answer, the smallest value we get for y is 0. So we'll say the range is 0 and on up. That's our domain and range. Now, is it a function? It actually is. The radical problems, we're going to study these in the next few sections. Radical problems graph to make a little arc looking thing. It looks like this actually. It starts at a half and it's an arc shape. And so arcs, these square root functions, no x is repeated, so yes, they are functions. All right, so that's how we handle the radical. Okay, our next example, well, actually, I think I'll save these to just a minute. Let's go down to the other one that's a function here, example E. Let's talk about that. So whenever we try to graph y equals 5 over x minus 1, again, I feel like most of us start graphing and plug in 0, 1, and 2, or we try to plug in 0, 1, and 2. Those are usually easy numbers to work with, although they're not magic. You plug in whatever you feel like and you feel like graphing. When I plug in 0 for x, let's see what y is. 0 minus 1. So 0 minus 1 is -1. 5 over -1 is -5. That's okay. That is real. So that's a real answer for y. So we can say 0's in the domain. Let's try plugging in 1. Y equals 5 over plugging in 1 for x. 1 minus 1. Try typing that on your calculator, and it's going to give you a big error reading, because when we divide by 0, that's actually undefined in math. It's not imaginary, it's just not even defined. It's not even math. There's no way to reason that out. So anyway, it's not a number, so we cannot use that. We do not get a real answer when we plug in 1. And again, that's because of this denominator issue. If you have a fractional function, anything that would make the denominator equal 0 has to be excluded from the domain. Now, we can keep kind of exploring here, plug in 2, 3, maybe try a fraction, a decimal, any other number that you can imagine is actually okay. I know I'm not giving you time to develop that idea, but let's just try the 2, just to proceed a little bit more. Plug in 2 for x, and you get 5 over 2 for x would be 2 minus 1. 2 minus 1 is 1, and that's good. 2, 5 is a real point you can plot on this. Maybe try plugging in 3 and 4. Let's try plugging in 6. 6 gives me a nice even result. It's okay to get a fraction answer. They're real, you know, fractions are real, but they're harder to plot, I guess. So sometimes I shop for a point that's easier for me to graph. So I can see 6 would kind of do that for me. 6 and 1 is a nice point, a real nice crisp plottable point. So actually anything, if you want to plug in 1,000,000, -1,000,000, square root of 5, Any other number that comes to your mind is okay with this fraction situation. The only thing to watch when it's a fraction function is this denominator cannot equal 0. So how are we going to write that domain? Really, like I said, anything could be plugged in except for that 1. Whatever makes the denominator equal 0, exclude it. So it'd say negative infinity up to 1, and then we use a parenthesis, because parentheses means we don't include that value. We just get really close to it, the fractional amount up to it. Then we say union, and then 1 on to positive infinity. So that's our way of writing the domain, meaning everything except the 1 that makes the denominator equal 0. Now the range, the value you could not get over here, is kind of a different argument for this. And again, you could plot a lot more points to kind of see the pattern here. But you can't get an answer of 0 in this fraction because there's a 5 in the numerator. And the only way to get y equal to 0, this side the range to equal 0, is to have a 0 divided by something. Well, since there's a constant there of 5, it's never going to be 0 divided by something. There's no variable to make us plug in a different value. It's a constant 5. So 5 divided by anything is going to give us a fractional amount or a whole number amount, but it's never going to make a 0. We cannot achieve a 0 answer when there's just a constant on top of your fraction there, and there's nothing out here to add or subtract to it. It's just never able to equal 0. So our range, we write, the only number we can't get for y in the range is 0. And that's a typical example if you were doing a fraction, domain, and range. Now the fraction functions, we're going to learn this one as well later in the semester. This is going to be a function graph. There's no repeating on the x, and again, if we take more time on all these, you kind of get in the quick version of it. We could plot a lot more points to see that this is true. No x ever repeats. All right, so those are the two big things to watch out for. Radicals, you take what's under the radical and say that has to be greater than or equal to 0. And then the other biggie with domain and range is the fraction one. When you have a fraction, you set the denominator equal to 0. Whatever makes that equal 0, you have to exclude it with a parenthesis and union it. All right, these other two are examples of non-functions. All these other three examples were all functions, but these two are not functions, and so they won't come up as much, but there are non-function examples. Anytime y is to an even power, that's actually going to make a sideways parabola, and we could plot some points to develop that, plugging in for x and getting for y, but it makes a sideways parabola when the y is squared. So the vertical line hits it twice. So this one is not a function. Now we can still give its domain and range though. The domain, so I'm just going to give you the picture of it to go from the domain and range. So again, it's a sideways parabola. So the domain would start here from left to right. Domain is left to right, 0, and it touches 0, and it goes to positive infinity. For the range, it opens up and down. This is going up and down without bound. The range is infinities. And then for this other example, anytime you have an inequality, it's called an inequality symbol, a less than or greater than. Those are never functions because you actually shade like a whole section, like you did in chapter 1 a little bit. You'd shade a section. So you're shading, you would draw this line. It looks linear because x is to the first and y is to the first. So it is a linear like base of it. But then because of inequality, you shade one whole side of this line. So let's say this looks sort of like this. And then you find out which side is shaded either above or below the line. This one lines up shading below. So it's definitely not a function because when you draw the vertical line, it's hitting it, just all kinds of space there, so not a function. All right, so that's the main thing I would say, examples that you need to know proceeding in 2.3.